multi-viewport object tracking. So let's define the problem statement over here. We need to make sure that if an object is in the scene, we need to first identify it, then track it within the scene. And we also need to make sure that even if the viewport changes, we need to track it across different viewports. So let's see how it is done. We will break the problem into three sub problems and we will optimally solve it. So let's see. First, we need to identify the object. So in this context, I'm keeping my object as a human. So what we need to do is we need to make sure that the human object is identified. So we will be using a boosted ADA cascaded classifier with linear binary partitioning for the features. In my original concept, I had given that I'll be using a HOG, histogram of gradients, for my features, but it is computationally expensive. So we'll be preferring with LBP. Then we need to make sure that the object is tracked within the scene. And we also need to make sure that it is done in real time. And we know that LBP is made up of integer calculation. It uses a sliding window and it does integers calculations. So it is really fast. And we know that we'll be using the tracker called generic object tracking using regression networks, which is cited in the Goten paper. And this is, mind you, it's a offline training neural network. That is, it is already pre-trained. So we only evaluate the neural network to find the optimal solution. So it is really fast. So we almost get about 10 to 15 FPS using the first person identification using LBP. Then the neural network also offers significantly high performance. So once we cascade both these algorithms, we might expect a good performance even in an embedded platform. But the performance hit comes only when the viewport changes. We will be using a person re-identification algorithm to make sure that the object is tracked consistently throughout all the viewports. So let's see how it is done. We'll be using a person re-identification algorithm called local maximal occurrence representation, and we will be evaluating it using cross-view quadratic discriminant analysis, which is also cited in LOMO and XCUDA evaluation. So we will be using a sliding window over the object, and we will be using local features extracted using histogram of gradients, and we will be evaluating using cross-view quadratic discriminant analysis to make sure that the objects within the viewport are consistent across different viewports. So let's see how it is done. In LOMO, that is local maximum occurrence representation, we will be making sure that we will extract the Hawk features. Then we will be evaluating using cross-view quadratic analysis, and we will find a rank. The rank needs to be not exactly the same, but it needs to be within a significant threshold to make sure that both the targets are ID'd appropriately. Then what we will do is we will find the probability that the object is the same from the two different viewports. Then we assign the appropriate ID. For example, in this context, we have seen the yellow shirt in ground floor has been tagged as number 1. Then as he moves across the viewport, he's again tagged in the first floor as number 1. So that's how we need to make sure that the problem statement is solved.